Here's a picture of the beginning of chapter 10, I think. That's the Hale-Bopp Comet. So this comet was discovered in 1995. You guys were already born in 1995, weren't you?
Yeah, 1 year later.
Really? Oh, wow.
When will it pass again?
Well, I don't know. We can probably figure it out. So the Hale-Bopp Comet goes around the sun. It's not a planet because it's too small, and its path is not like the planets that orbit around the sun. So it's called the comet, and it has a specific path, and the path has eccentricity of 0.9951. So that's very close to 1. What happens when your eccentricity is close to 1? Does it look more like a circle, or what's the other shape? It's kind of almost looks like a parabola. So probably when people looked at the path of this, they might have imagined a parabolic path. But since it came back again, then they probably figured it was an actual comet with an elliptical path. They give us information about the eccentricity, and then they also give us information about the major axis, which is 356.5 AU. What's AU? Like astronomical unit? Is it the distance to the sun? AU. So, whatever that is, it's 356.5. And so I think this picture should look something like this. We have the sun as your focus point, your focus. And then this comet goes around the sun. It spends most of its time probably out of the Earth's view, far away. You know, the other planets probably revolve around the sun just around like this, and then this comet does something that's a little bit different. So it's I just kind of messed up the drawing, but the major axis, if we try to look at this from a two-dimensional point of view, the major axis would go through the two vertices of the elongated side of the ellipse and would pass through the focus point, the sun. And so what we want to do is we want to let the sun be a focus at 0, 0, and then try to come up with an equation of the comet, or the path of the comet. All right, so the only thing we have is the eccentricity. We also have the axis, but we have the eccentricity. So we know our polar coordinate function would look something like this. It's E times D, was it? Divided by 1 and plus or minus E cosine theta. So let's use the plus side, and then we'll designate the directrix on the other side of the axis. So the tricky part is that we have this long distance over here from one extreme to the other of the path. So we don't have the directrix itself. So what happens is that in terms of trying to find these values, we have a slightly modified version of this function. And somewhere in your book, we have this information. So polar equation with an ellipse with a focus at the origin and semi-major axis A, eccentricity E, and then the directrix D. So what happens here is that they use some of those equations that we have to find the equation of the directrix. And basically the original equations that we had with x squared over a squared plus y squared over b squared is equal to 1, something like that. And then they replace the value of the directrix with the eccentricity and with the length of the semi-major axis. And so here's a nicer formula for us to deal with instead of trying to find the equation for the directrix. Okay? So it looks like the directrix D would be can be written in terms of the eccentricity and the length of the semi-major axis. So we can just use this formula, I think. So if we do that, we know our eccentricity and we know the length of our semi-major axis. Oh, this is a 5. So A is equal to 356.5. And so we could just plug it into that formula to get the path of our comet. So we have R is equal to A, 356.5 times 1 minus 0.9951 squared divided by 1 plus 0.9951, and then the cosine of beta. Okay. So the numerator will end up just being a number. And we can calculate that if you want, but I'm probably good with this particular answer, and that should work out. Any questions? All right, let's see if we can should we plug it in? Let's plug it in. R is equal to 356.5 times 1 minus 0.9951 squared divided by 1 plus 0.9951 times cosine of theta. Oh, they want to figure out how close does it come to the sun. Well, let's submit this first. And see if it'll take it. Oh, bummer.
This is round.
round each value 4 decimal places. All right, so $356.5 times 1 minus 0.9951 squared, 3.4832. .4851. What else do we need to do? Any ideas? Do we use the formula correctly? Oh, half of that. Okay, thank you. Semi-major. So A is equal to, what's half of that? So that can make a difference. So let's try that. Just divide it by 2. 1.7426. Does that sound right? 1.7426. Okay, so we got it, that part right. And then it's asking how close to the sun does it come. So we're looking for this distance over here. From the focus point. We can probably do some math to try to figure out what the coordinates of the outside things are. We can definitely graph it to try to see where it crosses the x-axis, and that's probably going to give you, when an angle of theta is equal to 0, it's probably going to give you that value. So to try to figure out what this is, we can try to figure out what r is equal to when theta is equal to 0 in your formula. You guys want to try to do that? No. Okay. Well, another way to do this is they have another formula in the book. The perihelion distance from a planet to the sun is equal to this, and the aphelion distance. So the perihelion distance is the closer distance, and the aphelion distance is the farther distance. So we have, if we use this formula, to help us find the closest and farthest distance, we can have a little shortcut formula for these things as well. Oops, where's my pen? So the shortest distance from the planet to the sun, in this case we're looking at a comet, is going to be given by the semi-major axis, times 1 minus the eccentricity. So we can figure that out. The semi-major axis that we found was 178.25, and then we multiply that by the 1 minus the eccentricity. And then we'll get our value. Okay. So whatever this is equal to should be the shortest distance. All right. So let's go past this idea of now identifying an ellipse using polar coordinates, and let's bring this back to a parametric equation. And we have a formula to translate our polar coordinate functions into parametric equations. You remember that formula? Okay. So let's get this. Let's get this number 1, because I'm going to be interested in graphing this. So let's graph this. R is equal to 1.74257 divided by 1 plus 0.9951 times cosine theta. So if the sun was at the center, this is how your ellipse is going to look like. It looks like a parabola, huh? But you can see its farthest point is about 350-ish, 300 and something astronomical units from the sun. That's 355.67. So that's how far it goes. What we might be interested in is in terms of tracking this, we can try to figure out how long this thing takes to go around the sun, so we can make a parametric equation out of this. So we can see this as a polar coordinate, or as a polar function, but if we can try to track it down as a parametric equation so we can put a timestamp on it, then that might work out for us a little bit better. So what I'm interested in doing is, I guess I have to go into, what's that called? Wolfram alpha, to try to figure out how long it takes for this thing to revolve around the sun. What's it called again? Hale-Bopp? What? Bopp? What kind of Bopp? Hale-Bopp Comet. No, this is some sort of, let's put comet. Oh, currently it's 38.35 astronomical units away from the Earth, and its current distance from the sun. Looks like it's fairly close. So we're at Julian years. Is that, what's our calendar? It's Gregorian calendar, but is it Julian? So it takes 2,534 years for this thing to pass.
I'm not going to give that.
So wait, if the next time for us to see it is that, what's a Julian calendar? So it's a regular Earth year, Gregorian years. So, all right. So let's use that as a time period. So let's say it takes that much time to go around the sun. That's your orbital period. And our function, let's take a snapshot of our function. And our graph, let's just draw our graph instead of trying to take a picture of the actual graph. And and just for simplicity's sake, we can mark t is equal to 0 to be this time period where the comet is closest to the sun. I guess where it's closest to the sun is over here, huh? I guess along this axis. Let's just call that a time period of 0. So what we're interested in doing is we're interested in rewriting our function as an x of t and a y of t function, so we can represent it in terms of parametric equations. So do you remember how to do that? So what's x of t going to equal to? So it'll be r cosine theta. So this is r right here. So we would have to rewrite the whole thing. We'll say 1.74257 divided by 1 plus 0.9951 cosine theta. So that's your r. And then you're going to multiply that by cosine theta. And then likewise, you'll change your y into 1.74257 divided by 1 plus 0.9951 cosine theta. That's your r again, but this time with the y, you're going to put sine theta. Okay? So how long do you think this is going to go around the sun? What's our theta limits going to be? But if we left our equation like this, what's our theta limits going to be? 0 to 2 pi, right? So from 0 to 6 point something, this is going to make one revolution. But our task is to try to make the revolution take not 6.28, whatever 2 pi is, but 2,534. So what do we need to do to scale that, or to rewrite our function so that it takes this long to go around? Any ideas? I guess I put t's here. Maybe I should have put t's here. Any ideas? So that instead of going from 0 to 2 pi, I actually want it to go from 0 to 2,534 units, in this case, years. What do we need to do? You understand what I'm asking? So if you have a circle, and your circle goes from 0 to 2 pi and makes a complete circle, what if I want to slow that circle down? I want to finish my circle by the time I instead of 2 pi, I want to finish it at 4 pi. Divide by 2 or multiply by 2? If you multiply by 2 faster, how about if we look at it this way? I'm going to do a little trig refresher here. This is the sine function. What does the sine of 2 theta look like? Is it squished or does it get expanded? It gets squished, right? And then I could draw the other part, but I just care about finishing one period of this. And so if I finish one period, this is going to finish sooner. This is going to finish at pi. And then if I want to take a look at the sine of theta over 2, what's going to happen there? It's going to get squished or going to get expanded? It's going to get expanded, so this time it's going to take twice as long. It's going to go to 4 pi. Okay, so I guess the question is about the period. I want to change the period so the period doesn't go from 0 to 2 pi. The period doesn't go to 2 pi. The period is 2,534. So there's this coefficient b next to the angle and the sine that we need to change. So what do I want to change that to? So if I want to change that to have a period of 2,534, I want to finish one complete loop by that. This is going to be sine of something times theta. So what's that something that goes there? Do you understand what I'm asking? Do you remember this from trig? I don't remember any of this. Divide by 2 pi? Yeah, so there's this number b that you would put in here, right? And then the period is going to be given by, what's the period given by? 2 pi over b. So if we want our period to be this number, 2,534, and is equal to 2 pi over b, so what's that coefficient b going to change into? B is equal to 2 pi over that really big number. All right? So what we're going to do to adjust this is we're going to change our theta, and that's all of our theta, not just the sine and cosine outside, but the cosine theta inside as well. We're going to change all those thetas so that we have the appropriate period. So we're going to rewrite our function 1.74257 divided by 1 plus 0.9951 times cosine of 2 pi theta divided by 2534. That's your R, and then cosine, and then you'll do the same thing, 2 pi theta divided by 2534. Okay? So once you have that, you can parameterize the path using now this parametric equation. So you would write the same thing here. I'm just going to copy it. And then multiply this by sine 2 pi theta over 2534. Okay? So, any questions about this so far? All right, well, let's actually see it in action. Let's see if we can see this working in our graphing calculator program. This is our function, and then we want to make it into a parametric equation function. So for my particular graphing calculator program, I need to change this now. If I draw this, it's not going to be that helpful because it looks like I'm just going to draw the same thing. Oh, it can't graph the equation of this form. Oh, because I need to change ahead to t's. So if I let my t go from 0 to 2 pi, I see that I'm graphing the whole thing again. But we changed it, right? We changed it to something else. So let's change this equation or this parameter into 2 pi t. Oh, did I put theta there? I think I put theta. What was it? 534. So I need to do that for all the t's. And now it's not going to graph anything because why? What? Why is it not graphing anything? Because I'm only going to go from 0 to 2 pi, so that's like 6 years or something. So let's go, is it 2,500? So let's just go 2,000 years. It looks like I finished it. Let's go at 1,000. That's about. Huh. It only went this far. 1,500. Whoa. Add 500 years. So it traveled that much for 500 years. Whoa. And then what if we put 1,200 years? So let's actually see it. Let me change my setup over here, and I'm going to take advantage of using the slider again by changing my t values into a's. And then let's let a equal to these possible values. Can't graph, really? No, I think well, this is just a two-dimensional point. It's A. What if we do this? What's wrong with this? Oh, there it goes. So let's, sorry, taking a long time here. Let's draw that path all the way around, and let's let A be the number of years. So it looks like between 0 to, let's say, about 1,000 years, you're still pretty close to the sun, and then it looks like it could possibly be speeding up as it goes outside of the sun, and then comes back a lot quicker. So I don't know if that's the actual path of the comet. That seems kind of weird that it would really go that much faster when it's farther away from the sun. But that's how we can use a parametrization to see the path as the values of t change, as time changes. Okay? So for your extra credit, remember that extra credit? 1 point for you to come up with an equation of the Earth's path in polar coordinates. So you'll get another extra point. So now this is for the second point, if you're able to parametrize it. And then parameterize it using basically the methods that we're using here. So you're really just rewriting your polar coordinate equation into parametric form just by using the formula r cosine theta and r sine theta. But I want you to use the number of days that it takes for the Earth to go around the sun, right? So it's like 365.25 or something like that. But again, you can use Wolfram alpha to figure out the exact amount of days. Okay? All right. So next time we're going to jump to chapter 12. Three-dimensional stuff, and we're probably going to get into vectors as well.